I'm Larry Wasserman. There's Ryan Tibshirani, who will be your teachers, entertainers throughout the term. We have a big cast of characters here. So we have 4 PAs and all of that information, and a course assistant named Mallory. All of that information is on the web. So the website is right here, www.cmu.edu. Go to Larry, that's an equal sign, equals SML. All the handouts are there, the course schedule, when the assignments are due, the assignments, how to reach the TAs and so on. We're also going to have one of those piazza.com things so that you can talk to the TAs through that website in addition to their office hours. I'll post these TA office hours as well, which I haven't done yet. And also, I guess on Piazza, you guys can talk to each other as well. So I realize most of you would probably have not printed out either the first lecture or the syllabus. So it's okay, don't worry about that. I'll write slowly today and clearly. Those of you who have taken 705 from me know how neat I write on the blackboard. So let me tell you what's in the syllabus, and then you can, at your leisure, just download it and see all the details yourself. So first of all, it's got the wrong course assistant, so I'll correct that. But let's talk about prerequisites. Technically, you should have taken 705, which is Intermediate Statistical Theory, and 10715, Advanced Machine Learning course. Now, I realize not all of you will have those prerequisites. Some of you may have taken 701 instead of 715, for example. If you want to take this course and you don't have the official prerequisites, that's fine with us. However, you have to make sure you do any background reading that you feel you need to do to catch up on the material that you may have missed. Okay, so it's okay to take it without the prerequisites, but just be forewarned that you should be willing to go and fill in any missing stuff that you need to do the course. But especially 705, if you haven't had 705, you really want to make sure you go and review some math stat stuff, because we're going to assume this stuff. We will do a review today and Wednesday about the basic stuff like bias, variance, trade-off, and so on, but it'll be a pretty cursory, fast review, and we'll be jumping into technical details pretty quickly starting next week. So things that you should know. You should feel very comfortable if we say something converges in probability or converges in distribution, law of large numbers, central limit theorem, maximum likelihood, Fisher information, Bayesian inference, regression, bias and variance, linear classifiers, and basic linear algebra. So all those things should be pretty familiar to you. You should feel comfortable with those things. There's no text, but we will be posting detailed lecture notes, and in fact, if you go to the website, you'll see there's already several chapters up there, and there'll be another one going up probably later today. So you can either print them out or bring your laptop, whatever's most convenient for you. There's going to be, is it 4 or 5 assignments? 4 assignments. Is that 4? Yeah. 4 assignments. Due Fridays at 3 o'clock. And you'll hand them into Mallory. I realize the syllabus has all the wrong dates in it, so if you do have access to the syllabus, I'm going to tell you right now, I'm going to post a new version with the correct dates because the dates of the midterm and so on are not quite correct. So there's 4 assignments. They're clearly marked on the web page. There'll be 1 midterm right before spring break. There is a final project, and there'll be some milestones along the way, like a progress report and so on. I'll get more to the project in a minute, and Brian, please jump in if I forget to say anything. Programming, there'll be a little bit of programming. This is mostly a theoretical course. So I should say that right at the beginning. Somebody complained about 705 being too theoretical, even though it was a course of theoretical statistics. So I just wanted, maybe I wasn't clear at the beginning there. That was a theoretical course. This is a theory course. Doesn't mean we do just theory, there's methodology and so on, but we are emphasizing the theoretical aspects of things. But there might be a bit of programming. You can use whatever language you want. Most of you probably use MATLAB. This is a good time to switch to R. Still time for enlightenment. By all means, collaborate on the homework, but when it comes to actually writing up your solutions, the actual, write-up should be your own. So work together, then go and write up your solutions on your own. And that's the homework. What else? Course calendar is on the web. Okay, so the project. So you've done many of your projects in other courses, and this will be similar, but the emphasis here is more theoretical. The idea is to kind of write a NIPS paper. So most of you know what a NIPS paper is. If you don't, go to nips.cc and look. You'll see all the NIPS papers, and you get a feeling for what they are. They're 8 pages long. They're in a very specific format. And the idea here is to actually kind of write some sort of review paper, in a sense, about a theoretical topic of your choice. You do not have to do new theory. If you do, that's great, but that's not required for the course. That's what you do for your thesis. It's not required for the course. So the idea is you pick a topic, like let's say you're interested in support vector machines. And the idea would be to write a paper summarizing what's known about these things, what they are, what are the known theoretical results, what are the conditions needed to make those results true, and so on. So imagine if you were writing, somebody asked you, can you explain support vector machines to me in 8 pages and what's known about them? That's what your goal is, basically. It's basically a chance to read a bunch of the current papers, absorb some of the theory, and summarize it. Okay? And we're going to do something a little bit different this year. Well, first of all, we encourage you to work in teams of 2. If you want to work on your own for some special reason, you can make the case, and if you have a good case, we'll certainly allow it. But we would prefer you work in teams of 2. And we're going to do something different. What we used to do at the end of the course was have spotlights. Everybody got up and got 2 minutes to present their project, and it was kind of fun. And we even had like a little shocking device. So if you went over 2 minutes, we give you like a shock, and there was all kinds of fun stuff like that. But just kidding, we didn't actually. This year we're going to do a bit differently, because that's a real rush. It's kind of fun, but it's a bit of a rush. So instead what we're going to have is where everybody submits their projects, and then you're all going to get to vote on the best one. So it's going to be kind of like your NIPS reviewer. So not only do you write the NIPS paper, but you're going to be like a NIPS reviewer, getting to pick which papers get accepted in the NIPS. And we'll accept some subset of them for oral presentations. And the last 2 days of the class will be kind of like a mini conference, where the people whose projects have been selected will be able to give maybe, I don't know what we decide, 15, 20-minute presentations or something like that. So it'll be like a little conference. We'll talk more about that as time progresses. And the syllabus gives you details about how you should structure the project and so on. All right. Let me see. Is there anything else on the syllabus? I think that covers everything. Ryan, anything you think I have missed? Any questions? All right. You're probably all wondering when the first assignment's due. I know you're hungry for that. So the first assignment is due tomorrow. Seriously. Just kidding. No, it's due a week from Friday. Okay. But download it right away and start working on it. Don't leave it till the last minute. And the TAs will be having office hours. We have office hours and so on, so there's lots of opportunities to get help. And I don't know how that Piazza thing works exactly. So at some point they'll get emails or something like that telling you you're all enrolled. June, do you know how it works?
No. We can enroll all of the class. The link that got is on the website, so if you're not enrolled, you can just enroll.
Well, the link I put was only to piazza.com. Don't they have to do something to get to this class?
I can update that.
We'll figure that out. And then that's a way, again, so in addition to office hours, this is a way to ask each other questions or ask TA questions. Good. Then if there's no questions, we're going to jump right into the review. And again, I know most of you do not have this. If you do have it, you can follow along here. If you don't have it, don't worry. You can download it when you get home. And in the meantime, I'm going to write slowly and clearly. And I'm going to review a lot of stuff pretty quickly. But remember, this is just review, so I'm kind of assuming this already feels familiar to you. There might be 1 or 2 things that we'll talk about that we haven't really gone into detail yet that we'll return to later in the course. But the basic ideas that I'm going to talk about here, you should feel very comfortable with. And then Ryan's going to do more of this type of stuff on Wednesday. Now I need to find a chalk brush or my sweater. Let's see if there's something hidden back here. Ah, there is on the other side. Oh, one other thing. These lectures are being taped, and we're going to put them up on YouTube so that if you want to go back and look at stuff, or if you miss a lecture or whatever, those lectures will be available for you. We'll put links there for you. All right. So let's start with a few items from probability. Managed to cram all of probability into this one paragraph here, so let's see how it goes. So one thing we use a lot are notions of convergence. So remember that we have something that we use a lot is sequence of random variables converging in probability to something, often 0, but it could be something else. And what does that mean? It just means the distribution is getting more and more concentrated around 0, or whatever it's converging to. So that means that the probability that xn is bigger than epsilon goes to 0. Because n goes to infinity for any epsilon. Okay, so we use that a lot. The other type of convergence we use a lot is the notion of weak convergence, or what we call it 705 convergence and distribution. So remind you that xn converges in distribution to x means that the CDF of xn converges to the CDF of x, right? So the probability that xn is less than t is this for all t? No, all points t at which this CDF is continuous. Good. And of course, you remember that the main probability theorem associated with this type of convergence is the law of large numbers, and the one with this type of convergence is the central limit theorem. The other notation we use a lot is bounded in probability. So xn is, let's say, big OP. Roughly speaking, this means this is sort of less than or equal to this in probability. Or more precisely, we can always find, you give me an epsilon and I'll find some big constant such that xn over an is less than the constant with high probability. So probability would say this is bigger than m for all large n. Right? You give me an epsilon, I'll find a big constant m such that this is true for all large n. It means that xn divided by an is not shooting off to infinity, right? It's kind of staying in place, bounded in probability. So we use that a lot. And the other one is little o p, which is that xn is little op, and just means that xn over an is going to 0 in probability. So think of big O as less than or equal to, and little o is strictly less than. Okay. Hopefully all that's going back now. Law of large numbers. What's that say? That x bar n converges in probability to mu, here mu. So the convention will always follow is if we don't say otherwise. When we talk about something like x bar n, remember that's computed from a sequence of random variables. And if we don't say otherwise, we always assume the sequence of random variables is IID. If it's not, we'll certainly tell you.
Xn over n converges in probability to 0 or 1?
This is mu.
No, above that. Xn divided by n converges in probability
To 0.
to 0? Not 1?
Not for little o.
Okay.
Any other questions? Okay, so remember, this is actually the weak law of large numbers, which is the one we use the most. There's also the strong law, which refers to almost sure convergence, but mostly we use convergence and probability. And then, so I don't want to get too far to the extreme, so tell me if this becomes unreadable at some point. Can you see this over there? Yeah, okay. So remember the central limit theorem says that x bar n minus mu over sigma converges weakly to a normal 0, 1, where sigma is the variance at xi. All right, so there you go. 1, 2 blackboards. We've managed to squeeze all probability theory in there. All right, so those things, again, should be very familiar, and we're going to use them all the time. Let's now talk about a little bit about statistics. Something that Ryan will talk about on Wednesday quite a bit is various versions of bias variance trade-off, which plays a big role. Let me just mention the basic fact. Remember that if I have some estimator, so I'm using the same notation for 705, anytime we estimate something, we put a hat on it. So this is actually a random variable, and it's a function of some data set, x1 to xn. And it's supposed to be estimating, let's say, some fixed quantity theta. And the basic result that we used quite a bit was that the mean squared error broke down into two pieces, the bias squared plus the variance, where bias is the mean of the estimator minus the truth, and the variance is just the variance of the estimator. So there's all kinds of different little variations on this when it gets to regression and classification and so on, which Ron will talk about in detail on Wednesday, which you've seen in 705 and you've seen in 701 or 715, but it's good to go through it again because there's a lot of different versions of the bias variance trade-off, and since we use it a lot in this course, we'll spend some time reviewing it. And remember, one of the big things in statistics and machine learning, especially in prediction, is there's always this tug of war between the bias and the variance. And typically we're trying to choose some sort of classifier or regression estimator. And if it's too flexible, the variance will get big, and if it's not flexible enough, the bias will get big, so we're trying to always balance those two terms. All right. When dealing with parametric models, and I should say a lot of this course will actually be dealing with non-parametric methods. But when we're dealing with parametric models, the main method we learned for estimating things was maximum likelihood. So what is a parametric model? It's some set of densities actually, here's a place where statisticians and machine learners often differ in their notation, so I should just clarify this. There's some random variable here, x. That's what's random. And for whatever reason, the tradition is a little bit different in both fields, is that the p sub theta, a lot of times in machine learning, people write the random variable here. That's not what we're writing here, right? The random variable here is x. This is, I could rewrite this as maybe this way. There's some parameter. Think about this as like the mean of a normal distribution. So the random thing is x. Theta is just an index. It's just the parameter indexing the family of distributions. So that's, unless we say otherwise, that's what that notation means. And then the most common method for estimating the parameter is to compute the likelihood function. Let me write it like this. And as you know, we used the likelihood for a source of testing and confidence intervals and estimates. In particular, theta hat, the MLE, is the maximizer of the likelihood, or equivalently, it's the maximizer of the log likelihood. It's usually easier to maximize the log likelihood, and of course you get the same answer. So that was our most commonly used estimator in parametric settings, not in non-parametric settings. And we always computed this quantity called the Fisher information. It says the Fisher information based on n observations is n times the Fisher information based on a single observation. And the latter, I'll just write the scalar version of this. It's just the expected value of the second derivative of the log density. If this was a vector theta, we'd have a Fisher information matrix instead of a single number. And the reason why we were interested in that, well, because if I define Sn to be 1 over that's an estimate of the standard error of the MLE. So one of the things we proved in 705 was that under certain regularity conditions, the MLE satisfies the central limit theorem. Not always, but assuming certain conditions are satisfied. And the reason why this is very useful is because we use this fact to say, well, we know the probability of a normal being between two numbers is 95%, and then we could substitute this and rearrange it for theta, and we got ourselves a confidence interval. So that was a fundamental thing we did, was to write down a random interval theta hat plus or minus remember what Z alpha over 2 is, right? It's just the right upper quantile of standard normal. So if this is a standard normal, this number, this probability. So this is a random interval because theta hat's random, and thanks to this central limit theorem, we know it's an approximate 1 minus alpha confidence interval, in the sense that the probability, and keep in mind, right, that this is random and this is fixed, and the probability that this traps this value versus 1 minus alpha. So that was one of our ways of computing a confidence interval, though of course we had other ways of doing it as well. Okay, let me pause and see some questions. Gotta ask questions, or I'll just keep going faster and faster. Pretty soon I'll be going at the speed of light and the whole course will be done yesterday. All right, then let's keep going. I'm taking this as a good sign. It just means we did such a good job in 705 and 715 that stuff is really stuck with you. All right, so let's talk a bit about regression, and again, Ryan will deal with this in much more detail on Wednesday. But in regression, we're trying to predict a real valued random variable based on something, let's say an RD. So X is the covariate or the feature, as it's sometimes called. We're trying to observe X and predict Y, and a typical way of measuring, let's call it the predictive risk of a function G, would be the squared error prediction risk. It's not the only measure of prediction risk, but it's the most common one. And if we try to minimize this over all possible functions G, so this is minimized by sure you're awake here.
By the regression function.
Yes, so it's minimized by m of x, I'll call it, the mean of y of an x, which of course is not known, so we have to estimate it from the training data. So when we talk about non-parametric regression, which we barely mentioned in 705, but we'll talk about quite a bit in this course, we'll talk about lots of ways of estimating this non-parametrically. You've seen the linear version where we restrict ourselves to linear predictors. So a linear predictor looks like this. Really, I should write beta 0 plus that, the intercept. But if we always agree that first x is a 1, then that already contains the intercept. So I'm going to do that so I don't have to keep writing beta 0 plus that. Okay. And then the prediction risk is this. And we can talk about what beta minimizes that without assuming that the true regression function is linear. There's still some beta that minimizes that. And in fact, it's given, so this is minimized by choosing beta equals to, I wrote it here as lambda inverse alpha, where lambda is just, it's a d by d matrix. What I've done here is, this feature vector is a vector x of length d. There's d features per person. And I wrote the brackets because I'm never quite sure how to distinguish the ith person. So the ith person, let's say, looks like this, but that's a d vector. So I didn't want to write x sub j for the jth feature, so I wrote it in like a bracket notation. So I mean the jth feature and the kth feature. And similarly, alpha j is the expected value of y. All right, so that's the best linear predictor. The true regression function is unknown. In fact, even the best linear predictor is unknown because it depends on these expected values, which are integrals with respect to the true distribution. But of course, we can estimate it from the training data. What are the data? The data are going to be pairs, and of course, this risk, what do? We approximate this prediction risk with the training error. And then, as we did in 705, we just said, well, let's minimize the training error to try to get this best linear predictor. And that, what did we get? We got the least squares estimator, which looked like this. What does all this double notation mean? So the reason for these double bars, there's a lot of x's and y's floating around here. What I've done here is written this funny looking y is supposed to represent the vector y1 to yn. And this funny looking x is what we usually call the design matrix. So it's just all the x's put together. So in other words, this is the first row. This is always the convention we'll use in this course. That the first row is the first person. So this is person 1, feature 1, person 1, feature d, and so on. The second row is person 2, feature 1, person 2, feature d, and so on. So this is n by d. Don't forget, the way I've written things, this is actually a column of ones, the first column. So I just made this funny or whatever you call this, math blackboard font to try to distinguish the random variable from the matrix. Just hope that's clear. Anyway, so you remember that's the least squares estimator. When could we use that though? Or better yet, when couldn't we use that?
In high dimensional space.
Yeah, in high dimensional setting, like if there's more covariates than observations, this isn't going to be invertible. So that's when we have to start talking about sparse estimators or ridge estimators, various things that you touched on in 701 and 715. And this is something else, of course, we're going to spend a lot of time on in this course, is the theory of sparsity. Last thing I want to remind you about here on basic least squares is that if we look at now the predicted values, by which I mean if I pump in, if I take each xi and I multiply it by the least squares estimator, I get a yi hat. So let's call that vector yi hat. Then that's just x beta hat, which is actually just what we call h times y. H is x. Remember this guy? This is called the hat matrix. This is a really important equation. This is the hat matrix, and what it says is that the predicted values when you do these squares are just the original values times this matrix, and it's easy to check that this matrix is symmetric and idempotent. So it's a projection. In fact, it's a projection into what? Into the column space of the design matrix. So these squares can be viewed as taking the original n data points, getting n predicted values, and there might be n of them that actually live in a lower dimensional, d-dimensional space, and the hat matrix is the projector into that space. We talked about that briefly in 705. We'll return to this point when we talk about smoothing and things like that. Okay, so that's the review of least squares. So I'm wondering, Ryan, I have this stuff now about bias, variance for regression, but you're going to do that in detail. Maybe I should skip it for now. Yeah. So the next stuff, if you do have the printout, you notice is stuff about the bias, variance chart in detail for regression, but Ryan's going to talk about that on Wednesday, so I think I'll skip over that. There's no point doing it twice. Let's just jump over to classification. In spirit, classification is the same problem. We've got some x's and we want to predict y. The only difference is y is discrete. And in the common case, the most common case, I guess, it would take two values, which we can call 0 and 1. And so what happens differently, of course, is we're not trying to predict a real valued thing, we're trying to predict a binary thing. So instead of a regression function, we're going to have some sort of classifier which takes an x and outputs a 0 or a 1. And we're probably not going to use squared error loss anymore for prediction. The most common loss function, or risk function, I should say, is classification error. The probability that you take an x and output a prediction, and the probability that you got it wrong. And once again, we should always keep in mind when we're using these different risk functions that there's a choice of risk functions. This is not the only risk function one can use, just like in regression, squared error isn't the only one. But this is the most commonly used one, so unless we say otherwise, we'll just assume we're using this prediction error. So the gain in regression, or sorry, in classification, is to somehow choose an x or an h to make this prediction error small. Just like in regression, we know there's a theoretical best predictor, which was the mean of y given x. We also know that there's, in principle, a best classifier, which is only, again, in some sense, a theoretical quantity because you'd have to know the true distribution to write it down. Let's remind ourselves what it is. It's called the Bayes rule. And as I told you, for those who took 705, that's a bad name because it has nothing to do with Bayesian inference, but that's the name. I didn't invent the name, so Don't blame me, but we're stuck with it. And it can be written in a couple of ways. The regression way of writing it is you classify as 1 or 0. Where m of x is again the regression function, the mean of y given x. Since y is binary, the expected value is just the probability that it's equal to 1. So sometimes people will write it like this. So a couple things to note. First of all, this shows you that classification and regression are kind of very intimately related. If you knew the regression function, you'd know the optimal classifier. Just compute the probability that y is equal to 1 given x. If it's bigger than a half, classify it as a 1. If it's less than a half, classify it as 0. It also gives you a way of producing classifiers, which is estimate the regression function, and then just insert your estimate in here. That's called a plug-in classifier. And many classifiers you've learned are actually plug-in classifiers, even though they might not have been presented to you that way. So for example, you probably know the nearest neighbors, k-nearest neighbors classifier, which is usually taught to you as, here's an x, find the k-nearest neighbors, and just take a vote. If there's more ones, classified as a 1, otherwise 0. But actually you can rewrite it as, that's a particular estimate of the regression function. It's actually a plug-in classifier. So many classifiers are explicitly presented as plug-in classifiers. And some of them are not written that way, but they could be rewritten that way. The other way, though, of writing this it's also, you can write it as 1 or 0 if pi1 p1 of x is bigger than and 0 otherwise, where pi1 is the probability, the marginal probability that y is 1. This is the marginal probability that y is 0. And these p1 and p0 are just the density functions. So this is the density for x among the cases when y is equal to 1. That is, or y is equal to 0. Probability of x given y equal to 0. And p1 of x is p of x. So that's an equivalent way to write this. And it also suggests a lot of classifiers. We can certainly estimate pi1 by just counting how many y's are equal to 1. So that's easy to estimate. And this p0 and p1, they're just density estimators. This is just take all the data where y is equal to 0, take those x's and estimate the distribution of x. And similarly for p1, and plug it into this formula. And again, many common classifiers turn out that they could be written this way. An example would be the linear classifier, where if these are taken to be, if we estimate these with normals, and plug them in, you'll get a familiar looking linear classifier for example. But of course, there's many other ways to do classification. Okay, any questions? All right, we'll just keep going. Good, really good. Now at this point, I want to recode the data. Instead of calling it 0 and 1, sometimes it's convenient to call them -1 and +1. Obviously, it doesn't matter what the labels are. There's two labels. You can call them cat and dog. You can call them A or B. You can call them 0, 1. So now I'm switching -1 to +1. It's just whatever's convenient. And when you write it this way, though, it has a nice feature because a lot of classifiers now have the form that the classifier is just the sign of some function, psi of x. Sign here with a G, not sign like sign code. Sign like +1 or -1. It's not the other sign. So you first get some function psi, and then you see is it plus or minus, and that gives you a classifier. So the example you're probably most familiar with here would be a linear classifier, which might take this form. So you first compute this beta, then you get the psi, and check is it plus 1 or minus 1. And why bother rewriting it this way? Well, just because so many classifiers have this form, and in particular it allows us to rewrite the risk, the probability that we misclassify an observation is really now just the probability that the sign of psi and the sign of y differ. If they're both plus, we're good, and if they're both minus, we're good. It's only when they differ. So this is really the probability that they have differing signs, or another way to put that is the probability that y times psi of x is negative. The only way that can be negative is if they have different signs. And that simple little trick is actually quite revealing, because if I think about this axis as being this quantity, just think of this as a single number, let's call it A. Then what's going on in classification, and what makes things computationally difficult, is that whenever this is negative, this thing is 1. Sorry, the loss, sorry, I left out a step here, the loss function. Let me write down the loss, which will just be the sine of y times minus 1. That's wrong. Forget that. Here's what I'm trying to say. When this is negative, the loss is 1. This is 1, yeah. This is 1 or 0. The loss is 1 or 0. When this is negative, the loss is 1. When it's positive, the loss is 0. Yes, that's all I wanted to say. Right? You either get it right or wrong when you classify. But when you see it as a function of this thing, which is sometimes called the margin, it's kind of revealing because it shows you, well, this is not a nice convex function, which, not surprisingly, it's going to be hard to minimize this thing because it's not convex. Hopefully you're all taking Ryan's course on convex optimization, so you'll, by the end of the term, be experts on how to optimize convex things. But this is typically non-convex. Well, it is not convex. So this is not an easy thing to optimize. And one thing we'll do a lot in the course, which is quite popular now, is we'll use a surrogate loss function, which is, let's take this nasty 0, 1 thing, and just put something like this that's convex and decreasing, and minimize that instead. That's called a surrogate loss function. You're taking the loss you're interested in and replacing it with something else. And what are some common choices for this? Well, if we write this one, that looks pretty much like I just drew it, up to artistic error. And if you minimize this, it turns out this is just maximizing the log likelihood function for logistic regression. And we'll talk about logistic regression. I'm sure you think you did it at 701 and 715. You can think of logistic regression as coming from a particular model, or you can think of it as taking this unwieldy loss function and substituting this smoother convex loss function, the surrogate loss function. Another surrogate loss function that's quite popular is this one. It looks very similar. Anybody know what this one is? If I minimize this instead, that's what's used in AdaBoost. AdaBoost uses that surrogate loss function. For those of you who have not heard about AdaBoost, don't worry about it. If it's important, if we decide it's important, we'll talk about it. These days, very popular one is the hinge loss function, which looks like this. I say these days because things change quickly. You know, neural nets were the hottest thing in the world when I was young. Then everybody decided they were, bogus. Now all of a sudden they're back in. So you never know. So this is the hinge. The hinge loss is pretty hot these days. It's the smallest convex surrogate, by which I mean it's of all convex functions that lie above this function, this is the in. And it looks like this. So that didn't quite come out looking convex, but pretty close. And if I minimize the training version of this, overall, let's say linear classifiers, what do I get? Support vector machine. That's all a support vector machine is substituting a different loss function. Okay, so we'll talk about all this in detail, and I want to conclude today with kind of a more conceptual thing. So the plan now is, I have this section in the notes you can look at when you get there, but we'll talk about it now. It's called Why Study Theory. I'm going to talk about this for a few minutes. Don't put your coat on yet, we're still talking. Just kidding. But I do want to talk about this question. And then again, on Wednesday, Ryan will talk about bias and variance and related issues and estimating risk and so on in more detail. Then, by the way, next Monday is Martin Luther King Day, so there's no class. Then we return on Wednesday and start doing the material on non-parametric density estimation. All right, so this last section of the notes is why study theory. This is a question that comes up. There are some people who don't think it's worth studying the theory. Most of you probably do, or you wouldn't be here, although you are required to take a course, so maybe that's not true. Some of you are required to take the course, so you're here whether you like it or not. But a lot of you are here voluntarily, and so I hope that means you think that there's value in studying the theory. It's pretty interesting, actually, to contrast the role of theory in statistics and in the machine learning community, because at the risk of oversimplifying, I think statisticians came from a background where they always made sure they had very rigorous theory framing method before using it, which was on the one hand a good thing, because then you can say this thing, here's how it works, these are the conditions you need, and so on. But it also really made statisticians very conservative and afraid to take risks and plunge in and try high-dimensional problems and so on. Machine learning had a little different history, which is people would just make up algorithms, try them out, declare success, and then do something else, which has all pluses and minuses. On the positive side, I think it's made machine learning move very quickly as a field. On the negative side, there is a little bit of this, I have my own classifier, and I've tried it on my examples, and it's better than everybody else's, let me publish it. And so now there's like 7 million different classifiers out there. It's not clear, does this one actually beat this one? Under which conditions does this work? I actually went to a talk once many years ago, where this guy presented this talk, and he said, and the reason why I do this with machine learning instead of statistics is because in statistics they make assumptions. So I put up my hand and I said, well, you're just not stating your assumptions, you're actually making assumptions. But I think that was, this is 10, 15 years ago, that was kind of an attitude back then, that by not stating assumptions, you weren't making any, which is a little bit misleading. So the reason why we do want to study the theory, well, for some people, of course, they're just interested in the theory. But even if it's not your primary concern, you still want to understand some of the theory. You need to know, when does something work, and why does it work, and when does it fail? Most importantly, why does it fail, and when does it fail? So again, there's millions of different classifiers. So how do you answer the question, when is this classifier better than this classifier? When is a support vector machine better than logistic regression? And these theoretical tools we learn at least provide some way of trying to frame the question, trying to answer it, trying to say, under these conditions, this classifier is better than this classifier. Under these conditions, this one's minimax and this one isn't, and so on. So it is actually a useful way to try to understand when and why things work. I really think the perfect example of this is deep learning. So right now, deep learning is very hot, and depending on who you talk to, it's either one of the best inventions in machine learning ever, or it's all smoke and mirrors. It's just people training complicated classifiers with millions and billions of data points. So I like to ask people, do you think it's something there, or is it kind of all scam? And you really do find that the opinions are quite split. So it would be nice if there was a theoretical breakthrough which said, yes, deep learning works better because of this, or under these conditions, or no, it doesn't work, and so on. We're still waiting. Nobody's really come up with a good theoretical explanation of deep learning at this point. A good example of this to me was AdaBoost, which was very mysterious at first. For those of you who don't know, It was a very hot thing for a few years, and it seemed to work really well, and there wasn't a good explanation. And then some statisticians, actually, as it turns out, Ryan's father and Trevor Christie, and I'm not just saying it because Ryan's in the room, but they wrote this great paper, I think, which really, to me, explained what AdaBoost is doing. It's just doing a forward stepwise approximation to this loss function. And you can see there was some follow-up papers that showed under what conditions it works and what conditions it doesn't work and so on. So I really think it's important to know the theory, or at least some of the theory, to really be able to answer the question, when does something work? Why does it work? It helps you answer questions like, how do you choose the tuning parameters? Tuning parameters are critical in all these algorithms. And so on. So that's kind of why, I think the understanding the theory is pretty important. And a lot of times we stated results in 705, and we'll do it here too in terms of minimax results, which is saying, given that I've made the following assumptions, which is the best regression function or regression method or classifier, meaning minimizing the worst case performance. Now, of course, you could choose other measures of performance, but at least minimax theory is a way of doing it. And as we saw in 705, there are very precise answers. So a good example of this is, well, here's an easy one, the sample mean. The sample mean is minimax for estimating the mean of a normal under any bowl-shaped loss function, for example. So that's a pretty convincing result. In density estimation, we're going to see that depending on what assumptions you make, we're going to be able to compute explicitly the minimax risk of, say, a density estimator or a regression estimator. And the importance of that is, if you've made up your own estimator, you can say, is it minimax or not? If it's not, you know there's something missing in your estimator, you can improve it. If it is minimax, you're done. There's no point in trying to improve it anymore. So these things are actually kind of important in practice. All right, so I think that's pretty much everything I wanted to talk about. And you might be hoping we're going to let you go early, but I think we're not. I think we should jump right into Ryan's stuff, unless there's any questions. Everybody's so quiet. All right, in that case, let's jump into the next set of notes, which unfortunately I did not post yet. I'm sorry about that, but I'll post them right after class.
Okay, so I hate to be the reason why you're not leaving early, but I think in the long run you'll thank me 10 years from now. You've learned 20 extra minutes of material. So last year, by the way, I did this thing where I tried to tell a joke every time I gave a lecture, and actually got kind of mixed reviews. I mean, people really liked it at the start, but then I couldn't keep up the quality of jokes and it went downhill. And so my jokes had to be about statistics or machine learning. That was the catch. All right, so at least we'll start this time. I may give up if they suffer in quality. And they're supposed to be corny, so you should laugh. But, all right, here's the joke. A statistician, a mathematician, and a physicist, they all go hunting. So if I can remember this. And the physicist, he sees the deer that they're trying to hunt, takes his rifle, and he aims, and it misses 10 feet to the left. And then the mathematician takes his rifle, and he tries to shoot, and he misses 10 feet to the right. And the statistician then puts down his rifle and says, "We got it." Okay, that's good practice. You have to make the laughter louder. Okay, so if you have this set of notes in front of you, then you can see that I wrote the top. You should pretty much know this stuff already, the stuff we're about to cover. But if you don't, then this is definitely important to see. If all of this is foreign to you, you should probably come talk to us for the TAs, because it means that you've missed some of the kind of major prerequisites. But most of this should at least be review in some sense. We'll get into some new stuff towards the end. All right, so we're going to talk about bias, the bias range trade-off, and statistical prediction. Okay, and a pretty generic framework. Okay, so I'm going to try to use the same notation that Larry used pretty much. So suppose we observe x and y from some unknown joint distribution. Right, x is some kind of feature, covariate predictor variable. We have many names for it. Y is the response, the target, the output. Again, we have many names for it. But the goal is we're trying to predict y from x. Okay, let's suppose that's our goal from now. And we're going to stick with this loss function for now. Larry wrote down this exact same expression, I think, just a moment ago. The expected value of y minus f of x, where f is some function that predicts y from x. Okay, so we're interested in at least characterizing this, which we call the prediction error, or the expected test error. And this expectation, by the way, is taken over the distribution of x and y jointly. And so here x and y are both random. This expectation is taken over both of those random variables. So as Larry wrote down just a moment ago, we know that among all functions, f, the guy that minimizes this is the regression function. So I think he wrote it down as m of x. Okay, so you've already seen this. Now here's something that I like to talk about right away, because I think some people see this and they think, very general. X and y from some joint distribution, I'm being very general. Then all of a sudden when somebody on a piece of paper writes this down, they somehow think this is a modeling assumption. There's some modeling assumption here, right? I've written y as f of x plus error. What? Oh, sorry. That's an important typo. Okay, so the question I'm going to raise first is this any different from what I wrote down on the left board? Can I always write this? I can always write this, right? It's going to let epsilon equal to y minus its conditional expectation given x. And we know from the properties of expectation that this is going to have mean 0. Right? The expected value of y minus the expected value of the conditional expectation of y given x, they're the same. Okay, so you should never think that because someone writes down a model like this, say, suppose I know some true function, this all of a sudden means that they're being kind of, they're assuming more than if we just had some joint distribution for x and y. But this is important. This is where things become very important. What do I know about epsilon and f of x? So they're both random, right? Does it follow that epsilon is independent of f of x? What do you guys think? How many people think yes? Okay, how many people think no? All right, so yeah, the answer is not necessarily. That's actually a big assumption. Not true necessarily. Right, what does it mean for epsilon to be independent of f of x? Well, let's consider a situation where actually there was another random variable, z. Okay, and x and z had non-trivial correlation, so they were not independent. And I could actually write y as a function of x and z together. Then what is this epsilon capturing? It has terms that depend on z, right? Because if x and z actually weren't independent and they both drove y, then I can certainly write this down, and it's certainly true that epsilon has mean 0, but this epsilon is going to have terms that involve z in it, right? Because I've missed some variable, some explanatory variable. And if epsilon has some z's in it, and I told you that z and x were dependent, then certainly these two aren't independent. So if the model is misspecified in some sense, which means that I've forgotten an important variable, this is not going to be true. So now let's go back to real life. Is it ever true that you've kind of written down all the relevant variables for a prediction problem? No. Right? You'd never fool yourself to think that I've gotten all the x's that are relevant for predicting y. So you should actually think this is probably never true in practice. Right? That's a very, very strict assumption. Okay, but why am I bringing that up? It's because oftentimes we'll think about x as fixed. And I'll think about, I observe samples. Let's say I'll write them as xi, yi. I equals 1 to n. And I'll pretend like x is fixed because it's easier for the theory that way. Even though x might have been random in the experiment, I'll think about conditioning on x, so I'll just treat it as fixed. And I'll write down a model like this. yi equals f of xi plus epsilon I. And I'll say that the epsilon i's are iid with mean 0. Right, and maybe I'll even write down their variance as sigma squared. Okay, why is this an offensive assumption, considering what we just said? Well, what if I had a random x model? So really I believe that this was true at each random x. Then what am I doing by assuming that the epsilons are iid? I'm assuming that epsilon is independent of x, right? Because this epsilon was associated with this x. Epsilon j was associated with xj. But I just said they're iid, right? So they all have the same distribution. Particularly the variance of epsilon does not depend on x. That's something I'm assuming. So I am making this offensive assumption. I'm not saying we're not going to make this. We're going to make this all the time because it makes theory easy. But I'm just saying that when you write this down, or when you see a paper with this in it, you should think, wow, this is actually a fairly strong assumption, usually called a homoscedastic model. I'm assuming that the variance doesn't depend on the x points. Right? And it's offensive or it's strict because it's kind of pretending like we have written down all the true variables that may drive the prediction of y. All right. Okay, any questions about that? So we'll get back to that, by the way, in detail for non-parametric regression. Non-parametric regression is an interesting case in which I'd say that probably half the theory assumes that the x points are random. The other half assumes the x points are fixed. And the ones in which we assume the x points are fixed typically make this assumption that the error is iid and the variance doesn't depend on the x points. The one that assumes the x points are random doesn't make that assumption. It just thinks that x and y are from some joint distribution. And the theoretical leverage that we have in either case is very different. So you'll find entire books, and I list them in the non-parametric regression notes, that assume one model, and entire books that assume another, and they don't always produce the same results because they're different assumptions. Okay, so now let's get real. Let's pretend like we actually have some prediction function that we fit f hat on training data. x1, y1, xn, yn. Okay, and these pairs of points are iid from some distribution. That doesn't mean that x and the errors are independent. This means that I observe independent samples. That's the difference there. And I use that to fit some function f, and I want to know how well does f predict y from x. So what I'll do is I'll compute the expectation of y minus f hat of x, where x and y are another sample pair that's independent of the training sample and has the same distribution. And this expectation is taken over the training data, which is x1, y1 through xn, yn, and this new point, x and y. So it's taken over both of those things. And we usually call this the expected test error. Okay, so why would we be interested in this? Well, there's two reasons, primarily. There's probably more also, but here are the two that we'll focus on. The first is model assessment. Assessment, which is to say, how well am I doing in absolute terms? Maybe your collaborator wants to know, how well can you predict a new point y from a new point x, given what you have already fit on the training data. In absolute terms, he wants to know, what's your prediction error like? That's called model assessment. And you may think that that's a little bit more relevant for classification, right, where that has kind of a universal scale. What's your misclassification rate in predicting y from x? Then the second one is probably more common these days, although you invariably always end up thinking about the first one. The second one is the one that we usually push first, which is model selection. So suppose I had a bunch of different f's, and I want to know which one to use. That could mean that I have f hat fit on the training data using one method, and another function, g hat fit on the training data using another method entirely, like support vector machines versus logistic regression. Or it could mean that I have a tuning parameter, right? I could be doing something like k nearest neighbors, and I want to choose k. So I try this for a bunch of different values of k. That's the model selection problem. And we usually choose the model to use based on expected test error. So that's also why it's important to know that quantity. So, okay, again, I'm assuming you've seen this, but we're going to go through it anyways. Because if you didn't understand this part, then I think a lot of what we say next is going to be confusing. This is a very important property to describe the expected test error. And it decomposes into 3 parts. Okay, so think about 3 different things. The first thing we should think about is, can we ever predict y from x with 0 error? Is it ever possible to get 0 error in predicting y from x, generically, if I have jointly distributed random variables x and y?
Well, if there's some randomness, then probably not.
Probably not, right? So what happens, what's the best function for predicting y from x? We know that one already, right? I erased it, but it's the conditional expectation of y given x. Does that have 0 error? It doesn't, right? If that conditional expectation has non-trivial variance, then it has non-zero error, right? So if you think about it in general for a joint distribution x and y, you're going to incur some error, because even the best method, which is the regression function, incurs error. And so that part is called the irreducible error. Or the Bayes error. And this also might be a place to point out that name is not a particularly good one, but that's what people call it. Okay, so that means there's something we can't explain, which is just the pure randomness in the observations. It doesn't matter what function we choose, even if we choose the best one. There's something we can't explain predictably. Okay, then there's another part, which is to say, what happens if the model class of functions that we're choosing for this prediction problem to fit f hat is very far from the true regression function? So an example is the true relationship between y and x is highly nonlinear. Y is some complicated nonlinear function of x. If I compute the regression function, that's what it looks like. But I choose to fit f hat via linear regression of y and x. Then I incur a particular type of error that's called estimation bias. Or just bias. Which means that, in a sense, the model class that I'm using for prediction, the one that I'm actually using to fit f hat, is not broad enough to encapsulate the true regression function. That's another source of error. And the third source of error is what happens if, when I go and I fit f hat on today's training data, and then I get endpoints tomorrow, and I use the same method, just with different data points, I get a very different f hat. I do it again the next day, I get a very different f hat. That's called estimation variance. It's the third source of error, which means that the estimator itself is very variable. Or variance. Okay, so this is spelling out the bias variance trade-off. So we typically don't call it the bias variance Bayes error trade-off because we can't control the Bayes error, right? It's just some number. We can't ever get smaller than that. Whatever method we choose doesn't affect this term. It's always there. It's some constant. Okay, so to make that mathematically precise, I'm not going to prove this decomposition for you, but you guys should be comfortable with how one would do that, and I can explain to you what the steps are in words. We're going to first write this as like this, where sigma where I'm going to write epsilon for y minus f of x. Remember, that's the regression function. And sigma squared is the variance of epsilon. Okay, so this is called the Bayes error, this part, or the irreducible error. And this part is usually called the risk or the MSE. So in statistics, we usually call it risk. You'll see it called MSE in machine learning, other places in statistics as well. How do I get this? Well, I literally just add in f of x and I subtract f of x here and I expand the square. The term that looks like the expected value of y minus f of x squared is this. The term that looks like the expected value of f of x minus f hat of x squared is this, and the cross term is 0. See, the cross term is 0 because the expected value of epsilon is 0. So it's an exercise that you can repeat if you're not sure about it. Okay, then the risk is what decomposes into the bias and the variance. Sigma squared plus the bias part. And I'm going to do this conditional on x. Okay, because it's usually easiest to do this conditional on x. Then we're going to integrate over x overall. And the notes I hand out that we'll post on the website, there'll be the steps in there in case this isn't clear. Again, I'm assuming that most people have seen this. So maybe I'll just do actually this whole thing conditional on x. So I'll make these little x's. Okay, so this is conditional on x equals little x. And I'm going to integrate over the density of x. So all I've done is I've conditioned on x. And this is the point at which I'm predicting to make things clear. So this is basically the risk at x if I were to predict at x. And the risk overall is just what I get when I integrate this quantity over the distribution of x. Okay, and then this guy decomposes into the bias and the variance. And the bias looks like the expected value of f hat of x minus f of x. This is the squared bias. Squared. And then the same thing, p dx. This is usually called, this is the bias, so this is the squared bias. And the variance is just equal to the expected value of f hat around its expectation. Okay, so this is an equality. It holds no matter what f hat is, holds no matter what the distributions of y and x are. All I assume was that these points were IID. The sample points over which I train and the testing point. Okay, so it always holds. We can always decompose it in this fashion. Roughly speaking, the reason we care about this is because for some, well, multiple reasons. First of all, this is kind of like a philosophy we take in general for modeling. Okay, and then we'll get more specific as we go on. But the philosophy is that the more complex the model is that we fit, the lower the bias is going to be. Because if it's complex, then it's going to incorporate a very large class of functions. So it's likely that the true function will lie close to our model class. Okay? But the more complex it is, the higher the variance is going to be. Because the more complex it is, the more parameters it's going to take to fit. For fitting more parameters, it's going to be the case that the variance is larger. And we're doing more on the training set. So it's likely that if I get a new training set, I'll get an even more different answer. So that's the philosophy reason. We'll also see that actually the bias and the variance are avenues to computing the mean squared error or the risk of particular estimators. So when we talk about kernel density estimation, for example, and we talk about kernel smoothing and non-parametric regression, we actually go ahead and we actually bound the bias and the variance individually. That's how we compute risk bounds for these estimates. It ends up actually being quite good there. We can get like a sharp bound on the risk. And from that, we can see how the parameters in the model, and in that case, it's the bandwidth for the kernel stuff, affect the bias and the variance. So we can see specifically, as I decrease the bandwidth in the kernel, which makes the model more complex, what happens to the bias and what happens to the variance. And we can explicitly characterize the trade-off there so we can see how the risk behaves as a function of that bandwidth. Okay, so that's more specific. And the last point to make is that even though I've written this down for squared error loss, it's important to think of this principle as a governing principle no matter what the loss is that you're choosing. So it's not going to be an equality if I had absolute error here. If I replace the squared by an absolute value, this is not going to hold per se. If I put in your favorite loss, like exponential loss or something for AdaBoost, again, it's not going to be an exact equality, but we have reason to believe that the same governing principle applies. Right? The more complex the model is you're fitting, the higher the bias. That's one source of error. The higher the variance if you have a very complex model. And if the model is not complex enough, then the bias is higher. It's just a governing principle that we can follow. Okay, so I think I'll stop there because the next lecture I'm going to go into detail about computing this and then optimism and so on, but it's a good place to stop. See you guys on Wednesday.